Dear friends, welcome to the fourth lecture of our differential geometry course, the Corona semester, spring of 2020. Today we will start chapter 5, namely the shape operator. And the first section is the shape operator of a surface M in R3. Okay. Well, first we need a uh, reminder. Let Z be a Euclidean vector field on a surface uh, M in R3. So what is this? This is a function defined on M, and it takes values in R3. Namely, actually, it takes values in the union of tangent spaces. So each at each point, this is an element. This is an element of the tangent space to R3. So it doesn't necessarily lie inside the tangent space of M. So a Euclidean vector field on a surface M is this. To each point of the surface, we assign a vector. Okay, so let's say this is the point, it's the surface M, and we assign this vector. So this doesn't have to lie inside the tangent space. Tangent space could be like this, but this vector doesn't have to lie inside the tangent space. All right, so we have a vector field, and then we define the following object. Actually, we defined this before, but we just remind. We define the covariant derivative of z at p along the vector, along a vector v. This belongs to the tangent space. Okay, so this vector v belongs to the tangent space. Okay, so it's a vector like this. Okay, as follows: the covariant derivative of the vector field along the vector v. V is a tangent vector at the point M, at the point P. This is just z alpha derivative evaluated at 0, where z alpha is this. Z alpha t is just actually z of alpha t, and alpha t, alpha is a curve, smooth curve with the following properties. At 0, it is at the point P, and the velocity vector is just the vector v. Okay, so this is a way of taking derivative of an object along a vector v, right? You just pick a curve, pick a curve, alpha t, so that at the point 0, your curve is at the point p. When t is 0, you are at the point p, and the velocity vector is just v at that point. This is how we take derivative of an object. In this case, that object is the Euclidean vector field on the surface M, which is Z. All right. The first fact about this is the following. Let the Euclidean vector field has components like this, I from 1 to 3. So here zi's are all functions from M to R, okay? Then the covariant derivative we have just defined is nothing but v evaluated on the function zi. These are just some real numbers at each point multiplied with the basis vectors ui's. Remember, ui is the vector field on R3. It is the constant vector, right? U1 at any point is just 1, 0, 0. U2 is 0, 1, 0. And U3 is the constant vector 0, 0, 1. Okay, at each point they assign these three basis vectors. All right, here is the proof. Proof is just, writing down the definition in detail. All right, so what is Z alpha T? As I wrote above, this is nothing but Z of alpha T, okay? And Z has this description, therefore this is just summation from 1 to 3. Okay, let me just write it here. Summation from 1 to 3. Z sub I alpha T, and then ui, the constant vector field ui. So the derivative of this object evaluated at 0 is what? Well, you just take derivatives of these functions, right? Evaluate at 0, and then you multiply with ui. But what is this object? This derivative of z of alpha t ddt, where alpha t is this vector, this curve. This is nothing but, if you recall, just the partial derivative of the zi along the vector, directional derivative of zi along the vector v, and actually this is just v of zi. We write it just this way, and then ui, and this finishes the proof. All right. Well, this is an very easy lemma, but it also shows the following. Here we defined the covariant derivative this way. So we use this auxiliary curve alpha. Okay. We would like to define the derivative of z along the vector v, but we make use of a curve, okay, alpha. For this to be well defined, of course, we know that this object should be independent of the choice of alpha. And this lemma shows that. Why is that? Because it shows that this object, although it is defined using the curve alpha, uh, here you see that there is no alpha, it is just given in terms of the vector v. Therefore, this definition is independent of alpha. Therefore, in a covariant derivative defined like this is an well-defined object. So let me just state this. This lemma shows that this object is independent of alpha, and thus uh, it is well defined. Oops, I don't need this. All right, now here we have another definition. Uh, we will define what's an orientable surface. A surface M in R3 is called or will be called orientable if if there is a continuous function u from M to R3 so that uh, UP is never zero and it is perpendicular to the tangent space of M for all points P in M. Okay. Uh, each choice of such uh, functions such function u is called an orientation on M. Okay, what are orientable surfaces? Examples: uh, sphere, plane, torus are all orientable surfaces. Let's see. For the sphere, uh, we have actually basically two orientations at each point of the surface. So I need to choose a vector which is perpendicular to the tangent plane. So something like this. Okay. No, it should not be like this. It should point upward. Oops. Okay. So this is one choice of normal vectors, a continuous vector field, Euclidean vector field defined on the sphere. It is non-zero at all points, and it is perpendicular to the tangent space at each point. So tangent spaces are like this. Let's say, okay, so here it is perpendicular. Okay, so okay, plane is an orientable surface. Here is a continuous normal field. At each point, I just choose this vector field. Okay. Similarly, the torus is an orientable surface. Again, I can choose a vector field like this. And here it points like this. So these are all orientable surfaces. Let me give you one non-orientable surface, Möbius band. Like this. Okay, Möbius band. This is non-orientable. Is non-orientable. In other words, one cannot choose a continuous vector field, Euclidean vector field defined on the Möbius band, which is uh, perpendicular to the Möbius band at each point. Actually, you can see this, how, if you start, let's say, with a point here, let's say a vector like this, okay, so it's pointing upward, and then it is becoming uh, downward. I should maybe like this. And when you come to this point back, you will get this time, okay, this vector. So just the opposite of this one. It is continuous up to this point, but at this point, you get exactly the opposite one. So it is not, it cannot be continuous. Okay. All right. Well, why did we define orientable surfaces? Because we need it for the next definition. If P is a point in M, is a point then for each tangent vector V at the tangent space P, the quantity so defined this way, the covariant derivative of U along the vector v, and you have a minus sign, where u is a unit normal, so like this, a normal vector, but it has to be unit normal vector field defined in a neighborhood P on V. So here what we defined the function SP. Okay, so SP will mean the shape. It's an abbreviation for shape. Okay. All right. Yeah. Okay. Uh, SP is will be called the shape operator of M. Okay, so what is this? This measures how the vector field, this normal vector field, moves as we move in the direction of the vector v at the point P. So you are at the point P and you move along the vector, tangent vector v, and you measure how fast u changes. This is not a number, so when I say how fast, you shouldn't understand a real number, but this is a vector also. So change in the vector u. So it is another vector. So let me just write it here. Note that SPV measures how fast. So I should put this in quotation because it's not a real number. The normal vector, of course, we can identify it with the tangent space, right? Because uh, normal vector and the tangent space determines each other. The tangent, maybe I should say plane, TPM, varies as we move from the point in the direction of the vector field or vector v. So for example, for a plane, what would be the shape function or operator? Well, on a plane, right, you are at this point, these are your normal vectors. If you move in any direction, okay, v, the normal vector won't change because there's a unique normal vector, okay. Therefore, the change is just zero. So for a plane, SPV should be identically zero, okay, for all P in plane and V vector in TP gamma. We will compute this function for some other surfaces also soon. Okay, but first we need a lemma. This will tell us what this shape operator in terms of the objects we have studied so far. Okay, so let me write the statement. For each point P in M, M is a surface in R3, the shape operator is a linear operator. So it's a linear map and it's a linear operator, means it is defined on a vector space. In this case, it is the tangent space, and it takes values in the same vector space. Okay, linear map and defined on a vector space with values in the same vector space for all P in M. So we claim two things. The values of this function at any vector also lies in the same tangent space, and moreover this function is linear. Okay, so we actually claim uh, two assertions. All right, well, here is the proof. Since U is a unit unit vector field on M, we have UP dot UP, the dot product of this vector with itself is 1 for all P in M. Well, so its derivative, right, along any vector will be just 0 because it's constant. So the derivative of this dot product is 0. But we know that dot product is derivative of dot product obeys Leibniz rule. So this is just the derivative of u times this plus u times derivative of u. So this is just 2 times up and then derivative of up. Well, this means what? This product is 0 for all, of course, P in M and V in TPM. Well, this means, hence, this vector, the derivative of up, covariant derivative, is perpendicular to up for all P and V. But we know that up is the, right, what is up? Up is just the tangent vector, sorry, the normal vector of the tangent space, and our vector is perpendicular to the normal vector, right? Therefore, our covariant derivative is a vector inside the tangent space. Hence, it follows that the covariant derivative of up belongs to the tangent space for all P and V. All right. For the linearity, This is the first assertion. The second assertion follows from the following. For linearity, note that uh, SP of AV plus BW, so for any AB real numbers and VW tangent vectors, we have this. What is this? This is by definition covariant derivative along the vector AV plus BW of UP, oh, right, of the, sorry, vector field U, normal vector field. But we know from the properties of covariant derivative that this is just A times, sorry, definition was minus of this. Therefore, we have minus this derivative is just A times derivative of U along the vector V plus B times derivative of U along the vector W. But this is just minus A times AVU minus B nabla WU. So this is just A times SPV, no, SPV plus B times SPW. Hence, SP is linear on TPM. So this finishes the proof. We have a remark. The map U from M to S2. What is this map? It assigns each point to a unit normal vector, right? Unit normal vector. The unit normal vector to M at P is called the Gauss map of M. Actually, one should be careful here. For a surface M, if it is orientable and connected, there are two choices of Gauss maps. If U is, say, if we have one vector Gauss map, then you can just choose minus of that map. It gives another Gauss map because to a plane there are two normals, right? If you have one normal vector, if you multiply with -1, you get another normal vector. So here one should be careful. So let me write it here. If maybe, okay, if M is orientable and connected, then each orientation, well, actually I don't need connectedness, orientable, then each orientation determines one Gauss map. So you have Gauss maps as many as the orientations. Okay. All right. And also note the following. Uh, so for any point in M, uh, both TPM and the tangent space to the sphere at the point UP are or have UP as their normal vectors, and hence they are parallel. Let me draw you a picture. Okay. Suppose this is my surface. Sorry. At any point P, here is my, let's say, tangent vector UP, and this is my tangent space, okay, TPM. Now Gauss map takes this surface M to the sphere. So yes, U takes this uh, S2 sphere. So UP is nothing but UP is actually is since this is a unit vector, I can regard UP as a point on the sphere because UP is a unit vector. Therefore, I can regard it as a point. And since these two vectors are parallel to each other, the tangent space to the sphere at this point, which is this tangent space, so T, at which point? At the point UP of S2. Okay, so this tangent space and this tangent space are parallel to each other. As vector spaces, I both regard these points as their origin. Therefore, as vector spaces, actually these are the same. So U takes the point P to UP and takes this tangent space to this tangent space, but as vector spaces, these are the same. And the derivative of this map, so the derivative of this map, U star at P, is defined at the tangent space to M at the point P and takes values in the tangent space UP of S2, but we just see that these two vector spaces are actually the same. So it's a map from this tangent space to itself, and this is given by remember how the derivative map of a differentiable map is given at any vector. Whenever you have a vector in this uh, tangent space, it is given how just d dt of u alpha t, and then t equals 0, right? Where alpha is a curve in M with value p at the point 0 and velocity vector v. Okay. Hence, by its definition, u star pv is nothing but the derivative of u along the vector v. So it is just this, and this is just the shape operator with a minus sign. So shape operator is actually nothing but the derivative of the Gauss map. Okay, this is the Gauss map which takes a point to its normal, to the normal vector at that point. This is the Gauss map. Gauss map. And shape operator is the derivative of this. So conclusion is this. The shape operator of an oriented surface. Oriented surface means it's an orientable surface, but an orientation has already been chosen. Orientation means choice of u. So u is chosen. So the shape operator of an oriented surface. So this is the surface where u is chosen. The is nothing but the derivative map of the Gauss map. Derivative of the Gauss map. All right. Let me do some examples. Let sigma be the sphere in R3, centered at the origin and with radius r. The sphere in R3 with radius r. All right. Let's compute the shape operator for this. What's the unit normal vector to the sphere? Well, at any point, let's say P here. What is the unit normal vector here? Sorry. So let's say this is the point P, and this is the unit normal vector. This is the origin. What is the unit normal vector? And here radius is r. So this point P has distance to the origin r units, and this is 1 unit. So UP is nothing but the vector P. I regard this point as a vector from the origin to the point P, but this has length r as a vector, so I divide by its length. So my UP is this, okay? In coordinates, this is just 1 over r times xi ui, I from 1 to 3, where P is the point P1, P2, P3 on the sphere. Then what is the covariant derivative of this vector field along any vector? Well, this is I just write up u which is p over r. So we have okay, let me just do step by step. P over r. R is constant, so it goes out. P and P is nothing but it has coordinates 1 over r, x1, x2, x3, or I should write it this way, xi times ui. And what is the derivative of this? Okay, 1 over r, and then this is summation over r v xi ui. And what is this? If the vector v has, let's say, coordinates v1, v2, v3, v of f is nothing but sum of partial derivatives of f with respect to xi multiplied by vi. So I just take derivatives, partial derivatives of xi with respect to all the coordinates x1, x2, x3 and multiply by vi. This derivative will be non-zero if I take ith derivative of xi, right? Jth derivative of xi is just 0 if I is different than uh, uh, maybe I should be more careful here. Okay, so let me write summation over j del xi del xj vj ui, but this is just Kronecker delta ij, right? This thing is just Kronecker delta ij. Therefore, this is just 1 over r times vi ui. Well, ui vi is just the vector v again, right? Ith coordinate of v multiplied by ui, and you sum them up. This is the vector v, so this is v over r. But yeah, okay, so this is the uh, covariant derivative of v with respect to, no, covariant derivative of u with respect to v. Hence, the shape operator at v is just, which was minus this, so it is just minus v over r. So that this linear map SP is the linear map given by scalar multiplication by the constant minus 1 over r. R is the uh, radius of the sphere. So we see that the shape operator of a sphere of radius r is a simple object. It is just minus 1 over r times the identity operator. Okay. Well, let P be a plane in R3. Then we have seen that then clearly SPV is 0 for all P in P and V in TPP. Why is that? Since uh, the unit normal vector field to P is a constant vector field, and thus SPV, which is the covariant derivative with a minus sign, since this is constant, it has to be 0. Okay. Uh, okay. U is constant. All right. So here, the normal vector field is constant. So if you move on the plane from a point to another point along any vector, um, the normal vector doesn't change. Therefore, the derivative is 0. All right. Here is an interesting example. So let C be the circular cylinder of radius 1. So C is the circular cylinder of radius 1. Okay, let's choose a point P, uh, P in the cylinder C, and let's say it has coordinates x, y, z. The tangent space to C is the span of two vectors, E1 and E2. E1, sorry, uh, okay, this is E1 and this is E2. So what are those vectors? Well, clearly E1 is the vector 0, 0, 1 at the point P if you want. And what is E2? Well, this is nothing but, let me write it down. If you are at the point X, Y, Z, it is just minus Y 0, X 0. Okay. How can you see this? Well, you can just, consider this. If you are at this point on the circle, let's say xy, the tangent vector here is what? It has to be perpendicular to this one, so it should be minus yx. Why is this? Well, the x coordinate is negative, y coordinate is positive, and for this one, both coordinates should be negative. X was already negative and y was positive. Now it is negative. So this is the correct choice. This is also perpendicular to this vector. but this is not the right choice. Y minus x. Sorry. Okay, now let's compute the shape operator. Then the covariant derivative of the vector field UP. I didn't tell you what is UP. Sorry. What is UP? Yeah. UP is this vector. So U, X, Y, Z. It is just X times U1 plus Y times U2, right? The normal vector is this. Okay, so the normal vector is like this. U. Okay. Actually, we could do the following. Say this is has radius r. Then, of course, this is not a normal. This is a normal vector, but it is not unit length. To make it unit length, we can do this. Yes. And then let's compute the covariant derivatives. Covariant derivative of u along E1. Well, E1 is the vector 0, 0, 1. So it is just the vector U3 of U. U is this x times U1 plus y times U2. And then we have 1 over r. 1 over r is constant, so it just goes out. And then I take U3 derivative of this. Well, how do we do this? We just take derivatives of the coefficient functions, right? Coefficient of x with respect to u3 is just 0. And for the coefficient function y has derivative again 0 with respect to u3. So you just get 0. So this is just 0. All right. However, the other one, on the other hand, so this means what? If you go along the vector e1, the normal vector doesn't change, of course, right? U is kept fixed. Therefore, the covariant derivative along the vector e1 is 0. This is what we have observed here. But for the other one, for the vector e2, it shouldn't be 0. It should be similar to the sphere, right? This is like moving on a sphere. Just consider a sphere inside the cylinder, which is tangent to the cylinder. Okay, and suppose it touches the point P, then E2 will be just the tangent vector of the equator of that sphere. And we know that in that case, the tangent, the derivative will be just as above we computed. Let's just do it again. So, okay, let me do it here. E2UP. What is this? This is just, well, E2 is this vector minus y x0 my vector is just x u1 plus y u2 1 over r. 1 over r is constant, so it goes out. Okay, now uh, so this is minus y times u1 x u1 plus y u2 plus 1 over r times x u2 x u1 plus y u2. This minus sign this goes out, so minus y over r, and then derivative x u1 plus y u2, and this is x over r covariant derivative along the vector u2 x u1 plus y u2. All right, so this is just minus y over r. What is the covariant derivative? Well, derivative of y with respect to u1 is 0. Derivative of x with respect to u1 is 1. So I'll just get here 1 times u1 plus 0 times u2 plus x over r. This time this derivative is 0. So x times, no, 0 times u1 plus 1 times u2. So what we see is uh, 1 over r times minus y u1 plus x u2. And what is this? This is nothing but the vector field, actually E2, right? Because E2 was that exactly. Yes. So hence the shape operator at the vector E2 is minus E2 over R. So this means what? As I move along the vector E2, the tangent space changes, this time at this speed. Minus 1 over r times the vector e2. All right. Well, there is one more example. I will not do this. The saddle surface M given by the equation M equals xy. Uh, I'll leave it as an exercise. Compute the shape operator at the point P, where P is this point, 0, 0, 0. Okay. Actually, the answer is this. It should be B u1 plus A u2. Later, we will come back to this actually and see how we can compute this. Okay, so let's say we stop at this point for today. I'll see you later.